Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for a review of integration techniques once you've gone through all the integration techniques that you normally go through in a Calc 2 or integral calculus course. Now, everything I'm going to say here is really rough rules of thumb. To be honest, integration is a heuristic method. That means basically that you have a good idea of how to start a problem, but there's no hard and fast rule to do every single problem. That's what makes integration so fascinating. There's so many different ways to tackle different problems that a hard and fast rule set is likely not to exist. But there's definitely some suggestions that helps out significantly. So let's start talking about how I would appreciate my students learning how to decipher or pull apart an integral and decide what method to use. The first thing you should do is start and think 2 steps ahead. That means take a look at the integral you've been handed and start thinking about the types of processes or the types of techniques that might apply to that integral, and also think about the ramifications of applying those techniques. Sometimes a u substitution looks really attractive until you realize the differential of that u, du, ends up being something that is going to be really difficult to work with. So you can at least quickly throw out a u substitution, that type of thing. So it's really good to think a step or 2 ahead when you're integrating to make sure that the direction you're heading in is a good direction or is even a viable direction. Now I go into the steps. The first thing you should really try to do is simplify the integrand if possible. This generally means use some type of trig identities or algebraic manipulations. In general though, most of that should already be done. You might run into the very obscure or random moment where you have, let's say, a natural log of e to the x or some silliness like that. That obviously would simplify down to just the integral of x dx. But more often than not, you're not going to have something that nice. So that first step, it's kind of rare that you're actually able to do anything in that first step, but just in case, take a look. You might be able to factor something, who knows? The next thing you should do is create a list of tactics. And this is a list of techniques. And I say here, make a list of techniques that will not work, and then list out the rest of the techniques that will work. I actually go through and list out every technique, and then I scratch out the ones that aren't going to work. There's only so many, maybe a handful of techniques, so it's not that difficult just to write them down very quickly and cross out the ones you know won't work. You'll be left with 2, maybe 3 different techniques that might work. And of those remaining 2 or 3 techniques that might work, you should tackle the one that you're most comfortable with. At the same time, you should always look a step or 2 ahead. So if you're most comfortable with trig subs, for example, you should definitely look a step or 2 ahead to see the ramifications of doing a trig sub. Finally, choose a tactic. You have this list of tactics remaining after you've created that list and crossed out the stuff that wouldn't work. And those tactics would be simple integration, u substitution, products of trig functions, which often is called trig integration. Then you have trig substitutions, radical substitutions, partial fraction decomposition, and integration by parts. Notice how I've written these. I actually write them in the order of my preference. So these are actually ordered specifically for me. For example, if you could just directly integrate something, do it. That's what this is. If you can directly integrate, do it. If you can do a u substitution and it looks beneficial, do it. If you have a product of trig functions, well then, start making the powers even if you can. So these tactics kind of go through and list out the way you identify that you can use that tactic and the advice that I give on how to implement that tactic. For example, simple integration. The way you identify that you can do simple integration is that the integrand is close to the derivative of a known function. This might be something like the integral of, let's say 1 over 1 plus e to the 2x or something like that, dx. Okay, so that looks like a 1 over 1 plus x squared to me. And so I might think, oh, great, that's probably the tan inverse. It's not, but that'd be wonderful if it were. But beside that point, the reality is if you can look at a form and say, gosh, that's almost like. So let's take a look at these. Simple integration. The way you identify that you can use simple integration is that the integrand is basically the derivative of a known function. Pretty obvious, right? You have the integral of cosine or the integral of secant squared or something like that. Then just do the anti-differentiation. Make sure you keep an eye out for simple algebraic manipulations or trigonometric identities. For example, you may see something like this and say, I don't know the antiderivative of the tangent squared offhand. And you would be absolutely correct. However, you do have a trig identity that tells you tangent squared is secant squared theta minus 1 d theta. And I know the antiderivative of the secant squared is the tangent. And I know the antiderivative of -1 is a negative x, or negative theta in this case. So just keep an eye out for trig identities, stuff like that, that you can manipulate to get to easier forms. The next one that I think is the easiest is U substitution. This is actually one of my favorites, and it's pretty much every other student's favorite as well. How do you know you can use U substitution? At this point, you should already know, but the integrand contains two functions and one is approximately the derivative of the other. For example, something like the integral of natural log of x over x or something like that, right? You can let u equal the natural log. Its derivative is 1 over x dx. So there you go. Or another possibility is that the integrand contains a composition of functions. Well, compositions of functions are really, really popular in Calc 2. So seeing that will allow us to say, okay, I'm going to let u equal the interior function square root of x, and then du would steal away 1 over square root of x dx, and then you'd switch methods at that point and you'd switch into by parts. So just letting you know, all of these methods I'm suggesting work in concert with each other. You start with a U substitution sometimes, and then you end with by parts or something else. The advice here is really important. Convert back to the original variable in the end if you're working with an indefinite integral. And very, very important, if you have a definite integral and you use a U substitution, be sure to change the limits of integration. That's critical. People often forget that, and that's like a rookie move, so don't do it. The next one in line, and again, these are in the order that I would prefer to use them if they're available, product of trig functions. This is just a specialized U substitution. If you're working on the Stewart calculus text, then this is its own section. If you're working on most other calculus texts, this is kind of folded into the substitution rule conversation. This type of substitution is very powerful if you have the integrand, which is a product of sines and cosines, or a product of secants and tangents, or a product of cosecants and cotangents. It's also very useful if you just have only one of these trig functions, but it has a power on it. For example, sine cubed of x dx. In this case, letting u equal the cosine is very powerful because it steals away a single power of the sine, its derivative does, that is, and it leaves you with the sine squared, which can be written in terms of cosine squared. So it's very, very powerful method. My advice here is kind of lengthy. Try a substitution that forces the other trig function to end with even powers after the change from dx to du. You want to steal away odd powers with your derivative, so you force even powers. Even powers are very, very, very powerful in trigonometry. Once you get to even powers, you just use the Pythagorean identities to change out that sine squared for a 1 minus cosine squared, or that tangent squared for a secant squared minus 1. But what if both powers on those trig functions are even? And this only pertains to the sine and cosine, by the way, but if they're both even powered, then you got to do the power reduction formulas or the half angle identities. They're the same thing. So just be aware that's going to creep in there. I don't write it here, but when you're dealing with the secant and the tangent, you have a lot of options. For example, if both powers are odd, a wonderful substitution is the secant, because the derivative of the secant will steal away a power of secant and a power of tangent, and now they're both even powers, and that tangent to the even power can be rewritten in terms of secants. So there's a lot of little subtopics I'm not really mentioning in this video, but it's assumed that you've seen them or know them by now. As with most integration techniques, these are all prone to extra U-subs and by parts methods. So just to let you know, one technique is not usually the only thing you do when you integrate. You usually, pardon the pun, but integrate a lot of integration techniques. A rarity, but it does happen if the arguments of the trig functions are not the same. So in other words, if you have a sine of 5x times a cosine of 2x or something like that, then you're going to have to use those obscure product to sum formulas from your trig course. Generally speaking, most professors will allow you some type of, they'll either provide you with those or they'll allow you notes. I don't allow my students notes, but I definitely would provide them with those formulas if it were an exam or a quiz. And finally, like I've mentioned already, some integrals require non-obvious substitutions. For example, the cosine cubed, that would require u equals sine. So just keep your eye out. It's basically powers of trig functions is what this method is all about. Powers of trig functions. Next in my laundry list of methods, and the one that I would consider to be the next most powerful or popular in my opinion, would be a trig substitution. And these are called specialized x substitutions because you're actually allowing x to be something, not u, but x. How do you know that you're going to perform a trig substitution or that you have the opportunity to perform a trig substitution? Well, you know you're going to use this method when the integrand contains the sum of difference of squares, and that could be under a radical or not, doesn't actually matter. And you'll use it where a simple u-sub would not have worked. In other words, if you could use a simple u-sub, you should. My advice, make an appropriate substitution for x to get one of the following Pythagorean identities. And you can see them all listed here. I'm not going to read them out. Another little note here, completing the square is sometimes necessary. So just seeing a sum of difference of squares is not the only reason why you would use trig substitutions. You would use trig substitution method if you also have a trinomial that you can complete the square on. The next one, again, is not one that is technically by itself in a section in a textbook. It's just another style of substitution called a radical substitution. This one is just a regular u substitution. You know you're doing this if the integrand contains a mixture of polynomials and a radical of the form nth root of something. In this case, you're going to let u to the nth power equal that function. Or in other words, you're going to let u equal this nth root of g of x. And then you raise both sides to the nth power. When you do that, it allows you to find du implicitly. In other words, the derivative of the left-hand side of this would be n u to the n minus 1, and then, because it's a differential, du, and then on the right-hand side, g prime of x dx. It just keeps your derivatives a little cleaner so that you don't have to deal with radicals. And that's why we call it a radical substitution. They can be very, very powerful and incredibly helpful, so I highly recommend that you practice these techniques. Again, going down the list in the order that I prefer to do these, my second to least favorite is partial fraction decomposition. Not because I hate partial fraction decomposition, it's just the amount of work needed to do a true partial fraction decomposition can be a little overwhelming at times. How do you know that you need to do a partial fraction decomposition? Well, the integrand has to be a rational expression. That is, it's a ratio of polynomials. It has to be polynomials. It can't be like a natural log of something over the square root of something. It has to be just polynomials. And you use it when a u substitution just won't work. If a u substitution would have worked, you should have done it. Some advice. This method often leads to integrals of the form 1 over ax plus b dx, which is 1 over a natural log absolute value of ax plus b, and then plus some constant of integration. Or it leads to the integral of 1 over x squared plus a squared dx, which integrates to 1 over a tan inverse of x over a plus c. A bit of a warning here. The degree of the numerator for the integrand must be strictly less than the degree of the denominator in order for you to use partial fraction decomposition. So if it's not the case, then do some type of synthetic or long division first, and then you might still have to use partial fraction decomposition. In fact, you likely will. Again, my advice, always try to use substitution before doing partial fraction decomposition because, well, you'd be wasting your time otherwise. Finally, the method that is my least favorite, not because it's not awesome, because it is awesome, but it's just a method that, well, you know when you're going to have to use it, but it's just not the method that I initially want to use. Integration by parts. You know you're going to have to use it, or it's likely an option if the integrand is a product of different types of functions. I also recommend that you only use this when all other methods fail. Generally, you're led down this road very quickly, so don't think that you're going to work for 10 minutes before you decide to start working on by parts. Generally speaking, if you have to use by parts, it's going to be pretty obvious. You'll just run right down the list, and U sub won't work, and radical subs won't work, and partial fraction decomposition won't work, trig subs won't work, none of that works, and so all of a sudden your only choice is integration by parts. Integration by parts is somewhat of a convoluted method, so here's my advice. Look for the ugliest part of the integrand that you can actually integrate, and let that be dv. If it turns out that everything within that integrand can be integrated separately, so in other words, it's like an x sine of x or something like that, you can integrate both of those. Well then, if it's a tie for what to integrate, then you switch gears and talk about what you want to differentiate. So if there's a product of functions and both can be integrated, then there's a tie. At that point, instead of choosing dv, choose u, and choose u to be that function whose derivative will eventually change forms. So if it was an x sine of x, I would choose u to be x because I know its derivative will change forms to a constant. And I would choose dv to be the sine of x dx. Again, I would do that because I can integrate both x and sine of x, so it's a tie. So then I switch gears and start talking about what I need to differentiate. And finally here, many integrals can be done using this method that do not match the product of different functions rule. For example, the integral of tan inverse or sine inverse or cosine inverse, all of those can be done using by parts. The integral of natural log can be done using integration by parts. Yet it's not a product of functions. So this tactic is a great tactic for a lot of situations, but again, it's generally the last one I kind of go for. To wrap up this overview, here's some final words of advice. Remember, most integrals require a combination of all those techniques above. If all else fails, try again, do something different, switch gears, try another technique. And lastly, integration is almost wholly a heuristic method and requires a lot of practice. You can always find counterexamples to the advice I've given here, so take this list as a quote-unquote flexible list of tactics. All right, I think that's all I'm going to say here in this video. I think in the next video, I'll go through maybe 5 examples just showcasing how I can apply these tactics to integrating or evaluating some given integrals. I'll see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.